Good morning, one and all. I'm Dr. Vadraju Shichandra, Assistant Professor, Maturi Venkata Subbarao Engineering College, Hyderabad. Today I'm going to present the outcome of a BTech project of my students evaluating road network connectivity in Bengaluru using GIS and connectivity indices for better urban planning. So coming to the introduction, sustainable road transportation is vital for urban life, focusing on efficient, affordable, and inclusive systems while reducing environmental and health impacts. Developing highly connected and accessible road networks is central to sustainable urban development. In India, road transportation dominates, accounting for 67% of freight and 90% of passenger movement, contributing 3.1% to the GDP. Among India's 7,933 towns, including 474 urban agglomerations and 51 cities with populations exceeding 1 million, only 18 cities had metro rail systems by the year 2021. Road mobility remains indispensable, highlighting the need for improved infrastructure to support sustainable urban growth. Understanding road structures, including connectivity, coverage, and spatial distribution, is key to advancing sustainable transportation systems. So Kansky and Dacon created various graph theory based indices to measure connectivity, which are commonly used in road structure research. Sahitya and Prasad utilized these indices to assess connectivity in Hyderabad and analyze road network coverage through network and intersection density metrics. Sarkar examined the road network structure in Coach Bihar district of West Bengal, looking at factors like connectivity, accessibility, and network efficiency. Kyung et al. Applied connectivity indices to study the road network pattern in Mongolia, and Daniel et al. Identified a significant correlation between connectivity and coverage indices. We have selected Bangalore as the study area, which is the capital of Karnataka in the southern India, which is also a major ITI and economic hub with a population of approximately 28.5 million as per the Census of India 2011. Bangalore has road infrastructure which is extensive, which includes national highways like NH44 and NH75, though traffic congestion remains a significant issue. Rail connectivity is also robust, with major stations such as Bangalore City Railway Station linking the city to various parts of India. And Bangalore is pivotal to the nation's economy, particularly for its technology sector, housing numerous tech firms and startups. Its significance is further highlighted by its diverse industrial base, including biotechnology and aerospace. So we have taken the Bangalore urban area, Bangalore South, and Anekal areas for the present study. So coming to the methodology, as we can see from figure 2, we have imported the road network map of Bangalore urban area into the ArcMap environment. Then we have created layers of nodes and links using network analysis toolbar available in ArcMap. Then we have identified locations for connectivity analysis. Then we have generated 2 kilometer buffer around the identified locations using buffer tool in ArcMap. Then we have completed the connectivity indices for each location. Then we have determined what is the aggregate transportation score for each location and also the various matrices. Then finally, we have prepared the spatial maps of various indices. So the figure 3 shows the map where the buffer locations are highlighted, which are used for the connectivity analysis. So the table 1 shows the list of various indices used in the present study. We have used 10 indices here: alpha, beta, gamma, eta indices, and by using these 4 indices we have determined what is the aggregate transportation score. Then we also determined what is the edge density, node density, network density, and what is the grid tree pattern in addition to the cyclomatic number. So coming to the results of the present study, as we can see, the descriptive statistics of various connectivity indices are given here, where alpha index is ranging from 0.02 to 0.13, beta from 1.05 to 1.27, and so on. In addition to this statistical analysis, we also done the spatial analysis of these various indices using geographical information system. So as we can see from figure 4, where it is showing the spatial maps of alpha and beta index. So alpha index quantifies the level of connectivity in a network by comparing the number of cycles to the maximum possible number of cycles. Its value generally ranges from 0 to 1. Whereas for Bangalore city, the alpha index is varying from 0.02 to 0.13, suggesting a network with relatively poor connectivity and limited resilience to disruptions. And the beta index measures overall connectivity by comparing the number of edges to the number of vertices. So a beta index value of 1 signifies a minimally connected network, similar to a tree structure with no redundant paths. So the beta index for Bangalore ranges between 1.05 to 1.27, indicating that the network has slightly more edges than necessary to connect all nodes, suggesting some redundancy but overall relatively no connectivity. And figure 5 shows the spatial maps of gamma and eta index. The gamma index assesses the connectivity of a network relative to the maximum possible number of edges. Its value ranges from 0 to 1. So for Bengaluru city, the gamma index ranges from 0.35 to 0.42, indicating moderate connectivity with a reasonable number of alternative routes. While the network supports relatively efficient movement, it is not maximally connected, highlighting potential for further improvements in connectivity. Whereas the eta index measures the average length of edges in a network, calculated as the total length of all edges divided by the number of edges. So this index provides insights into the spatial characteristics of the network. For Bangalore, the eta index ranges from zero point 0 to zero point 0.06, suggesting that the average length of road segments is relatively short, indicating closely spaced intersections and a higher density of nodes. The figure shows the spatial maps of cyclomatic number and aggregate transportation score. The cyclomatic number quantifies network complexity by indicating the number of independent cycles present. The cyclomatic number is ranging from 46 to 2672, reflecting a broad spectrum of network complexities from moderately complex to highly intricate systems. Whereas the aggregate transportation score is a composite metric that includes various network indices such as alpha, beta, gamma, and density measures. So it provides a comprehensive assessment of a transportation network's effectiveness. So a network that has an aggregate transportation score of less than 100 is considered to be less connected. One that is between 100 and 200 is considered moderately connected. And networks with a score of more than 200 are considered to be well connected. In Bangalore, an average transportation score ranging from 48 to 2674 reflects a wide range of network quality, from underdeveloped systems with limited mobility to highly efficient and well-connected networks, the characteristics of a developed urban areas. So out of the 36 locations analyzed in the current study, the buffer zones 30 and 31 are less connected, and buffer zones 15, 32 and 36 are moderately connected, and remaining zones are well connected. So the figure 7 shows the maps showing the edges and nodes created as part of this study, and a moderately connected network, and also a less connected network in the study. The figure 8 shows the spatial maps of edge and node density. Edge density measures the ratio of number of edges to the maximum possible number of edges in the network. It indicates the level of connection density within the network. So the edge density is ranging from 403 to 7320, which is suggesting a variation from moderately connected suburban areas to extremely dense urban centers. The lower value implies sufficient connectivity for less dense regions, while higher value indicates extensive connectivity with potential for increased congestion if traffic is not effectively managed. The node density refers to the number of nodes per unit area and reflects the compactness of the network. So the node density value is ranging from 354 to 6010, which is indicating a variation from moderately spaced intersections, which is typical of suburban areas, to extremely dense networks found in the urban cores. So the higher node density generally improves the accessibility and reduces travel distances, but may also increase congestion, particularly in densely populated areas. And the figure 9 shows the network density and grid tree pattern maps. So network density combines node and edge density to represent the ratio of actual to possible connections in the network, reflecting overall connectivity. So the network density is ranging from 17 to 215, which denotes a spectrum from sparsely connected networks typical of suburban or rural areas to highly interconnected urban centers. Lower network density suggests fewer connections and potential challenges in traffic management, while higher density indicates a robust network that supports efficient transportation and resilience against disruptions. The grid tree pattern is a metric designed to identify and categorize the structural patterns of a network. It assigns a value between 0 and 2, reflecting different network topologies. So the grid tree pattern, which is ranging from 0 to zero point 0.5, is considered to be tree or spinal pattern. 0.5 to 1 is considered to be grid pattern, and 1 to 2 is considered to be delta pattern. From the analysis, it is revealed that Bengaluru road network has a GTP value of less than 0.5, indicating a spinal pattern. Coming to the conclusions, the study provides a detailed examination of Bengaluru's road network utilizing graph theory, indices such as alpha, beta, gamma, and grid tree pattern. The result shows that the Bengaluru's network has a spinal or tree-like topology with fewer loops and modest overall connection. The aggregate transportation score showed significant diversity between areas, emphasizing zones with both well-connected and poorly linked networks. And these findings are critical for urban planners because they pinpoint major regions where road infrastructure has to be improved in order to support the city's rapid growth and reduce congestion. The report underlines the need for focused infrastructure development to enable efficient and sustainable urban mobility. Future research could also investigate factors like street width and population density to address accessibility more comprehensively. And integrating GIS with urban road network connectivity analysis has demonstrated enhanced results supporting more effective decision making. And these are some of the references that are used in the current study. And thank you for the time.